Hello, in this lecture we find out the area of the green shape. In the drawing we have a quarter circle, AOB is a quarter circle. Inside this quarter circle we have this green shape. And our mission is to find out the area of this green shape. The green shape is actually a right triangle DCB because this angle equals to 90 degrees. Angle DCB equals to 90 degrees. So in other words, our mission is to find out the area of the right green triangle, triangle DCB. In addition, we know that line segment OB equals to 2 units in its length. Line segment AD equals to line segment DO. Repeat again, our mission is to find out the area of this green right triangle DCB. So first of all, we know that AOB is a quarter circle, therefore this angle AOB is equal to 90 degrees in its size. The point O is the center of the quarter circle, and because of the fact that AOB is a quarter circle, it means that sides AO and OB are above the radii of the quarter circle, and we know that side OB equals to 2 units in its length. That is to say, the radius of this quarter circle equals to 2 units in its length, and therefore side AO, that is also the radius of the quarter circle, equals to 2 units in its length. We know that AD equals to DO. So if we define AD as x, then DO must be also equal to x because they are equal to each other. So AD plus DO, it is actually x plus x. But AD plus DO is AO, and AO equals to 2, it is the radius of the quarter circle. So in total, we found out that AD plus DO is x plus x, that is equal to AO, that is 2. So x plus x equals to AO, that is 2. X plus x, x is 2x, so 2x equals to 2. We will divide this equation by 2, and get that x equals to 2 over 2, that is 1. So side AD equals to x, that is to say it is equals to 1 unit in its length, and side DO also equals to x, that is equal to 1 unit in its length. In the next step, I copy the right white triangle DOB in a new page, and we'll implement the Pythagoras theorem on this white triangle, triangle DOB. Here by PT is a version from Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Side D of the white triangle equals to 1 unit in its length. OB equals to 2, it is the radius of the quarter circle. So actually, this is the right triangle DOB that I got from the original drawing. According to the Pythagoras theorem, in this right triangle DOB, DB square equals to DO square plus OB square. So I write it down. The square of the hypotenuse is DB square, and DB square must be equal to DO square plus OB square. Repeat again, according to the Pythagoras theorem, in the right triangle DOB, DB square equals to DO square plus OB square. DB, the hypotenuse DB is the missing side, so we leave it as it is. DB square equals to DO square. DO is 1, therefore DO square is 1 square, that is 1. plus dB plus OB squared. OB is 2, therefore OB squared is 2 squared, that is 4. So in total, dB squared equals to 1 plus 4, that is 5. dB squared equals to 5. Here we take out all of this equation and get that the dB equals to the square root of 5 units in its length. Therefore, this dB equals to the square root of 5 units. So I can write down the original drawing. This is side dB, that is equals to the square root of 5 units in its length. In the next step, we will do a construction, that is to say, we will complete this quarter circle to a circle. So I actually completed the quarter circle to a circle. In the next step, we will extend the radius BO by a straight line until it touches the circle. And we define the touching point of the extended radius BO with this circle, this point as point P. BO as a radius, it is absolutely a straight line. And when you extend a straight line by a straight line, the result is a straight line. Therefore, BP is a straight line. If you focus on the upper side of the straight line BP at point O, here the sum of the angles must be equal to 180 degrees according to rule 3, that states that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of BP at point O? We have this angle that is a right angle plus the missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. Anyway, we know that BP is a straight line, but BP is a straight line that touches the circle at 2 points, B and P. Any straight line that touches the circle at 2 points must be a chord. So B or P is a chord and BP is a chord. But BP or BOP is a chord that passes through the point O, that is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, BOP is the diameter of the circle. If BOP is the diameter of the circle, it means that BP is the diameter of the circle. So I write it down. We actually found out that the BP is the diameter of this circle. So BP is the diameter of the circle. In the next step, we will extend line segment CD by straight line until it touches the circle. Actually, by extending line segment CD until it touches the circle, we create here peripheral angle. This will be a peripheral angle because it touches the circle at 3 points, B, C, and the third point that touches the circle. So B, C, whatever, is a peripheral angle, but this is peripheral angle that is equal to 90 degrees in its size. And we know that any peripheral angle that is equal to 90 degrees in its size must be subtended on the diameter of the circle. According to rule 5, I'll repeat it again on rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees in its size must be subtended on the diameter of the circle. So, in the drawing we have peripheral angle MAN, and this peripheral angle MAN equals to 90 degrees in size, and therefore this peripheral angle must be subtended on the diameter of the circle. And indeed, this peripheral angle MAN is subtended on MN, on chord MN, that is the diameter of the circle. And because of the fact that I can implement rule 5 in our drawing. Why? Because in our drawing we have peripheral angle. After we will extend side CD, we'll get peripheral angle. After we extend side CD until it touches the circle, we create a peripheral angle BC. Whatever the first point, anyway it touches the circle. Therefore, we create peripheral angle that is equal to 90 degrees in its size. And according to 5, because of the fact that this peripheral angle equals to 90 degrees in its size, it must be subtended on the diameter of the circle. And because of the fact that it must be subtended on the diameter of the circle, it means that the extended side CD must touch the circle at point P and not in any other point. Why? Because if we touch the circle at any other point, we get a contradiction to rule 5, because we get peripheral angle that is a right angle and it is not subtended on the diameter of the circle. In order to avoid the contradiction, we get that the extended side CD must touch the circle at point P and not at any other point. Otherwise, it will not, the peripheral angle that is the right angle, it will not be subtended on the diameter of the circle, and it will be contradiction to rule 5. In order to avoid the contradiction to rule 5, the extended side CD must touch the circle at point P. You can see, indeed, the extended side CD touches the circle at point P. So we have here peripheral angle BCP, that is a right angle, and indeed it is subtended on PB, that is the diameter of the circle. What is the definition of line segment OP? Line segment OP starts from point O, that is the center of the circle, and ends at point P, that is the point of the circle itself. This is exactly the definition of a radius. Therefore, OP is the radius of this circle, that is equal to 2 units in its length. So, in the next step, I'll copy the right triangle POD in a new page and we'll implement the Pythagoras theorem on this right triangle triangle POD. Here by PT is a version for Pythagoras theorem. This is the right triangle DOP that occurs on the original drawing. According to the Pythagoras theorem, in this right triangle POD, PO square, that is the square of the hypotenuse, must be equal to DO square plus PO square plus, actually it is PD square, the square of the hypotenuse is PD square, this letter is D, not O, PD square equals to DO square plus PO square. So PD square, that is the square of the hypotenuse, equals to DO square. DO is 1, therefore DO square is 1 square, that is 1, plus PO square. PO is 2, therefore PO square is 2 square, that is 4. So in total PO square equals to 1 plus 4, that is 5. Here we take a root out of this equation and finally we get that PO equals to the square root of 5 units in its length. So actually, this line segment PO, the hypotenuse PO, equals to the square root of 5 units in its length. In the next step, we extend the radius AO of this circle by straight line until it touches the circle. And we define the touching point of the extended radius AO with this circle, this point is point Q. So what is the definition of line segment OQ? Line segment OQ starts from point O, that is the center of the circle, and ends at point Q, that is the point of the circle itself. So this is exactly the definition of a radius. Therefore OQ is the radius of this circle, that is equal to 2 units in its length. Here we can actually implement rule 11. Repeat quickly on rule 11. According to rule 11 is true in any circle. So according to rule 11, if chord AB intersects with chord CD at point O, here we have chord AB intersects with chord CD at point O. Point O is the intersection point between the two chords. Then in this drawing, the following equation will be true. That AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can actually implement rule 11 in our drawing. Why? Because in our drawing we have chord AQ. This is chord AQ that intersects with chord CP at point D. Again, chord AQ intersects with chord CP at point D. So I write it down. Chord AQ intersects with chord CP at point D. Therefore, according to rule 11, the following equation will be true, that AD times DQ must be equal to CD times DP. Repeat again, according to rule 11, we get that AD times DQ equals to CD times DP. Okay. AD is 1 times DQ dq in total equals to 1 plus 2, that is 3. So dq in total equals to 3. And it is equals to CD. CD is the missing side, so we leave it as it is. Times dp. dp equals to the square root of 5 units. So in conclusion, we should find out that one times 3 equals to CD times square root of 5. 1 times 3 is 3. So 3 equals to the square root of 5 times CD. Here we divide this equation by square root of 5, and finally we get that CD equals to 3 over square root of 5 units in its length. So this is side CD, and it is equals to 3 over square root of 5 units in its length. Our mission is to find out the area of the green triangle DCB. So in order to find out the area of the green triangle DCB, I copy the green triangle in a new page, and we find out the area of the missing side CB, according to the Pythagoras theorem. Here by PT is the relation for Pythagoras theorem. So assuming this is the right green triangle CDB that the common from the original drawing, our mission is to find out the area of this right triangle. Here we implement the Pythagoras theorem. According to the Pythagoras theorem, this right triangle DCB the square of the hypotenuse is dB square, and it must be equal to DC square plus BC square. dB is square root of 5, therefore dB square is square root of 5 square, that is 5, and it is equals to DC square. DC is 3 over square root of 5, therefore this DC square is 3 over square root of 5. 3 over square root of 5 square is 9 over 5. Again, 3 over square root of 5 square, that is DC square is 9 over 5 plus BC square. BC is the missing side, so we leave it as it is. So in conclusion, we found out that 5 equals to 9 fifths plus BC square. Here we subtract 9 fifths from this equation, and you get that 5 minus 9 fifths equals to BC square. Here we take, we multiply 5 by 5 and then we divide it by 5 in order to have a common factor with 9 over 5. So the numerator we have in total 5 times 5 is 25, so in total the numerator we have 25 minus 9 divided by 5, and it is equals to BC square. (25 minus 9 is 16, so in total this expression equals to 16 over 5. So 16 over 5 equals to BC square. Here we take out of this equation, and finally we get that BC equals to the square root of 16 is 4 over square root of 5. So BC square equals to 4 over square root of 5 units in its length. This is side BC or CB. That is equals to 4 over square root of 5 units. So in the next step, I copy again the green right triangle DCB in the new page, and we find out the area of this green right triangle DCB. That is the area that we are looking for in this question. So actually, this is the right green triangle DCB that I got from the original drawing. Our mission is to find out the area of this right triangle. So the area of the green shape equals to the area of this right triangle. The area of the green shape equals to the area of the right triangle DCB. And the area of any triangle equals to the base of the triangle times the height to the base over 2. We take the base of this right triangle DCB as DC, and the height must create 90 degrees with the base. So CB will be the height, because it creates 90 degrees with the base DC. The height is CB over 2. So the area of the green shape, that is the area of this right triangle DCB, is equals to the base of the triangle, that is DC. DC is 3 over square root of 5 times CB. CB is 4 over square root of 5 divided by 2. Here 3 times 4 is 12, and square root of 5 times square root of 5 is 5 divided by 2. 12 over 5 over 2 equals to 12 over 5 times 2. So it is 12 over 5 times 2 is 10. So the area of the green shape equals to 12 over 10. We divide both the numerator and the denominator of this expression by 2. 12 over 2 is 6, and 10 over 2 is 5. 6 fifths is 1.2. So in conclusion, we found out that the area of this green shape is actually the area of the green right triangle DCB is equals to either 6/5 square units, or in terms of numbers, it is equals to 1.2 square units. So in the next step, I will summarize the lecture. In this lecture, we found out the area of this green shape. So actually, in the drawing, we have a quarter circle. Inside this quarter circle, we have the green shape. The green shape is actually the right green triangle DCB. And our mission is to find out the area of the green right triangle DCB. In addition, we know that line segment OB equals to 2 units in its length, and line segment AD equals to line segment DO. And repeat again that our mission is to find out the area of the green right triangle DCB. So, in the first step, we know that AOB is a quarter circle, therefore angle AOB, this angle must be equal to 90 degrees in its size, and side AO must be equal to side OB. They are both the radii of this quarter circle, and therefore they are equal to each other, and it is given as a question that OB equals to 2. Therefore the radius of this quarter circle equals to 2. And AO also equals to 2, it is also the radius of the quarter circle. Okay? It is given as the equation that line 7 AD equals to line 7 DO. So if we define the length of this line 7 AD is x, then DO must be also equal to x because they are equal to each other. AD plus DO equals to AO. Again, AD plus DO equals to AO, and AO is 2. So AD is x, and DO is x. AD plus AO is x plus x, so x plus x equals to AO. But AO is 2, so x plus x equals to 2. So x plus x equals to 2, x plus x is 2x, so 2x equals to 2. Here we divide this equation by 2 and find out that x equals to 2 over 2, that is 1. So AD is equal to x equals to 1, and DO that is also equals to x equals to 1. Okay, in the next step, I copied the right triangle DOB in a new page and we implemented the Pythagoras theorem on this right triangle DOB. This is the right triangle DOB that I copied from the original drawing. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the sides of the perpendiculars. The hypotenuse in the right triangle DOB is DB, therefore the square of the hypotenuse is DB square, and DB square must be equal to DO square plus OB square. DB, the hypotenuse DB is the missing side, so leave it as it is, so DB square equals to DO square. DO is 1, therefore DO square is 1 square, that is 1, plus OB square. OB is 2, therefore OB square is 2 square, that is 4. So in total, DB square equals to 1 plus 4, that is 5. DB square equals to 5. We took a root out of this equation and found out that DB equals to the square root of 5 units in its length. Here, this is the side DB that equals to the square root of 5 units in its length. In the next step, we did the construction, that is to say, we completed this quarter circle to a circle. Okay, and then we extended the radius BO by a straight line until it touches the circle. We define the touching point of the extended radius BO with this circle, this point as point P. So BO is a radius, it is absolutely a straight line. And when you extend a straight line by straight line, the result must be a straight line. Therefore, BP must be a straight line. So we know that BP is a straight line. If we focus on the upper side of the straight line BP at point O, here the sum of the angles must be equal to 180 degrees, according to rule 3, that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of BP at point O? We have this angle, which is a right angle, plus the missing angle. In total, they must be equal, the sum of those two angles must be equal to 180 degrees, according to rule 3. Therefore, the missing angle here must be equal to 90 degrees in its size. Okay, so we know that PB is a straight line, but PB is a straight line that touches the circle at 2 points, B and P. Any chord that touches the circle at 2 points, any straight line that touches the circle at 2 points is a chord. So PB is a chord. PB is a chord that passes through point O, that is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, POB is the diameter of the circle, and if POB is the diameter of the circle, it means that PB is also the diameter of the circle. Here, I wrote down that PB is the diameter of the circle. Okay, in the next step, we extended side CD by straight line until it touches the circle. It is given as a question that this angle is right angle. And by extending line 7 CD by set time until it touches the circle, we can do peripheral angle. And according to rule 5, any peripheral angle that is equal to 90 degrees in its size must be subtended on the diameter of the circle. So this peripheral angle that is a right angle must be subtended on the diameter of the circle, and the diameter of the circle is PB. Therefore, by extending the set line CD by set line, it must touch the circle at point P and only at point P. Otherwise, we get contradiction to rule 5, because we'll have peripheral angle that is equal to 90 degrees in its size, and it is not subtended on the diameter of the circle, because the diameter of the circle is PB. So if the extended side CD will not touch the circle at point P, it means that we have peripheral angle that is equal to 90 degrees, and it is not subtended on the diameter of the circle. In order to avoid contradiction to rule 5, the extended side CD must touch the circle at point P and only at point P. Okay. In the next step, I copied the right triangle DOB in a new page, DOP in a new page, and represented the Pythagoras theorem on this right triangle DOP. Actually, this is the right triangle DOP that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle DOP, dP square equals to dO square plus PO square. dP square, that is the square of the hypotenuse, must be equal to dO square. dO is 1, therefore dO square is 1 square, that is 1, plus PO square. PO is 2, therefore PO square is 2 square, that is 4. So in total, dP square or PD square must be equal to 1 plus 4, that is 5. So PD square equals to 5. We took a root out of this equation and finally found out that PD or dP equals to the square root of 5 units in its length. This is line 7 PD, or the hypotenuse PD, is equals to the square root of 5 units in its length. Okay. In the next step, we extended the radius AO by straight line until it touches the circle. We define the touching point of the extended radius AO with this circle. This point is point Q. What is the definition of line segment OQ? Line segment OQ starts from point O, that is the center of the circle, and that's at point Q, that is the point of the circle itself. So this is exactly the definition of radius. Therefore, OQ is the radius of the circle, that's equal to 2 units. So here, we can actually implement rule 11. I'll repeat quickly rule 11. According to rule 11, rule 11 is true in any circle. So in any circle, if chord AB intersects with chord OCD at point O is the intersection point of the two chords, then the following equation is true. That AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can actually implement rule 11 in our drawing. Why? Because in our drawing we have chord AQ. This is chord AQ that intersects with chord CP at point D. Again, chord AQ intersects with chord CP at point D. Repeat again. Chord AQ intersects with chord CP at point D. Therefore, according to rule 11, the following equation will be true, that AD times DQ equals to CD times DP. Again, AD times DQ equals to CD times DP. And again, according to rule 11, we get that AD times DQ equals to CD times DP. AD is 1 times DQ. DQ in total equals to 1 plus 2, that is 3. And it is equals to CD. CD is the missing side, so we leave it as it is, times DP. DP equals to the square root of 5 units. So according to rule 11, we found out that 1 times 3 equals to CD times square root of 5. 1 times 3 is 3, so 3 equals to the square root of 5 times CD. Here we divided this equation by square root of 5 and finally found out that CD equals to 3 over square root of 5 units in itself. The missing side, this is the missing side CD, that is equals to 3 over square root of 5 units in itself. I repeat again that our mission is to find out the area of this right green triangle, triangle CDB. So I copied the right green triangle, triangle CDB in a new page and found out, according to the Pythagoras theorem, the left of the missing side CB. So actually, this is the right green triangle DCB that I copied from the original drawing. According to the Pythagoras theorem, it is right triangle DCB. The square of the hypotenuse is DB square, must be equal to DC square plus CB square. Again, DB square must be equal to DC square plus BC square. DB is equal to 5, therefore DB square is equal to 5 squared, that is 5. And it is equal to DC square. DC is 3 over square root of 5, therefore DC square is 3 over square root of 5 square. 3 over square root of 5 square equals to 9 over 5 plus BC square. BC is the missing side, so we leave it as it is. So actually we found out that 5 equals to 9/5 plus BC square. Here we substituted 9/5 from this equation. And finally found out that BC square equals to 5 minus 9/5. Here we multiplied 5 by 5 and then we divided by 5 in order to have a common factor of minus 9/5. So 5 times 5 is 25, so in total in the numerator of this expression we have 25 minus 9 divided by 5. So 25 minus 9 over 5 equals to BC square. 25 minus 5 is 16, so 16 over 5 equals to BC square. Here we took out of this equation and finally found out that BC equals to the square root of 16, that is 4, over square root of 5. So BC equals to 4 over square root of 5 units in itself. This is side BC, that is equals to 4 over square root of 5 units in itself. So our mission is to find out the area of this green shape. That is the area of the green right triangle DCB. So I copied the right green triangle DCB in a new page and we found out the area of this green right triangle DCB. So the area of the green shape equals to the area of the right triangle DCB. Side DC equals to 3 over square root of 5 units in itself. Side CB equals to 4 over square root of 5 units in itself. So the area of the green shape equals to the area of this right triangle DCB. The area of any triangle equals to the base of the triangles times the height to the base over 2. The height must get 90 degrees with the base. We choose the base as DC times the height BC. Why the height is BC? Because it gets 90 degrees with the base DC over 2. DC is 3 over square root of 5 times BC is 4 over square root of 5 divided by 2. 3 times 4 is 12. Square root of 5 times square root of 5 is 5 divided by 2. 12 over 5 over 2 is 12 over 5 times 2. 5 times 2 is 10, so the area of this green shape equals to 12 over 10. We divided both the numerator and the numerator of this expression by 2. 12 over 2 is 6, and 10 over 2 is 5. So we found out that the area of this green shape, it is actually the area of the right triangle DCB, is equals to either 6/5 square units, or in terms of numbers, the area of this green shape equals to 1.2 square units. Okay, thank you very much.